Okay, so in the last video, we finished by looking at this function right here, f of x equals 2x plus 1 times 3x plus 5. And we said if I wanted to find the derivative and I didn't want to use the limit definition, I could FOIL this out. It would become a polynomial, apply the derivative term by term by term to the polynomial, and in particular apply the power rule, and my derivative ended up being 12x plus 13. But then we said if these polynomials were only slightly bigger, that whole foiling and then combining like terms and all that would get really cumbersome. And is there maybe a better way to find the derivative of a product of functions like that? So I've kind of taken the liberty here. This is the product. We want to find the derivative of the product, and I don't really know what it is. But according to the limit definition, this is what it should be. F of x plus h, g of x plus h, minus f of x, g of x over h. Product, product. Just plug in the x plus h and the x. And now I want to see if I can manipulate that. And I would point out at this moment, if we were seated in class, I would pause and I would say, now what in the world should we actually do? Because I have no idea. But this is a video, so you know, if you want to think about, hey, what could I possibly do to try to figure that out and simplify it? Pause the video and ponder it. But since this is a video, I'm just going to keep going right now. That was your warning. Pause in 3, 2, 1. Okay, no. Now, I'm actually going to apply a trick right here. I'm going to drop my limit for right now, like usual, to kind of save room. And I'm going to say f of x plus h, g of x plus h. This is all over h. Now, I am going to say minus, I'll write it this way. F of x plus h, g of x, plus f of x plus h, g of x. So here, I literally just subtracted and added this arbitrary term, this f of x plus h, g of x. Why I did that? It's a trick and it's going to work. We'll see later on. But as long as I subtract it and then add it, I'm just adding 0 because I subtracted and added off. They cancel. We'll see why I do that in a minute, but this is the trick to making this work. And then I have the minus f of x, g of x, and I'm out of board space, which is unfortunate. Now here, I'm going to break this off. 2 terms, 2 terms. And I can rewrite this. This is ultimately a big sum and difference over h. So I'm going to rewrite this as this difference plus this difference. And I will get, here there's a common f of x plus h. So f of x plus h times g of x plus h minus g of x all over h, plus here there's a common g of x. So g of x times f of x plus h minus f of x all over h. And now we're actually done. Now I can apply my limit. And here, maybe I'll just do it this way again to save a little bit of room. Now we'll apply the limit as h approaches 0. As h approaches 0, f of x plus h becomes f of x. So that's just f of x. This, the limit as h approaches 0 of g of x plus h minus g of x over h, is the definition of the derivative of g of x. That's g prime of x. Plus, here, the limit as h approaches 0 of g of x, there's no h's in there. That's just g of x. Here, the limit as h approaches 0 of f of x plus h minus f of x over h, that's the definition of f prime of x. And now, we can say, well, what is the derivative of the product of 2 functions? It's f of x, g prime of x, plus g of x, f prime of x. And now I have a formula to calculate the derivative of the product of 2 functions. It's actually called the product rule because it works for products of functions. And I would point out, your book actually does this backwards, meaning it says f prime of x, g of x, plus g prime of x, f of x. It does them in reverse order. That is completely fine, And for those of you who may have taken AP Calc or something like that before, if you're used to doing this product rule backwards, that is completely fine. This is the sum, the order doesn't matter. The reason I do it this way is because I still remember being in Calc 1 a long time ago, and I can still remember memorizing this rule, and I had to memorize it in my head over and over the exact same way. First derivative of second plus second derivative of first. Product rule. First function, derivative of the second function, plus second function, derivative of the first function. This is the way I learned it. This is the way my brain has it memorized. And if I try to do it the other way, I actually confuse myself because my brain does it automatically. First derivative of the second, plus second derivative of the first. You are allowed to reverse the order if you want. It doesn't change anything. I'm just always going to do it that way. But to see if this works, you can test it out right there. So we have f of x equals 2x plus 1 times 3x plus 5. This is my first function. Maybe I'm just going to arbitrarily call this h of x now, so we can use this notation. That's f and that's g. What's h prime of x? What's the derivative? According to the rule, it's the first function, 2x plus 1, times the derivative of the second function. That's a linear function. The derivative is the slope, 3. Plus the second function, 3x plus 5, times the derivative of the first. That's a linear function. Derivative is a slope, 2. Combine like terms that distribute. 2x times 3 is 6x plus 3 plus 6x plus 10. Combine like terms, 6x plus 6x is 12x. 3 plus 10 is 13. And my derivative is 12x plus 13. This is exactly what I got right here. So again, ultimately, it doesn't matter which rule you use as long as you apply the rule correctly. I'm willing to bet in this case, doing this as foiling and then just applying the power rule is not all that challenging. So here you might be inclined to just go foil, power rule, done. But suppose we have something like f of x equals 2x cubed plus 3x plus 5 times x squared plus 6x plus 7. Find f prime of x. I could FOIL those things out. I'm not going to. Combine like terms. I'm not going to. Power rule each term. I'm doing none of that. Or I can apply the product rule. What's the product rule say? First function, 2x cubed plus 3x plus 5. Derivative of the second. I know I can apply the power rule term by term. X squared gives me 2x. 6x, that's linear. I get 6. The derivative of the constant is 0. Plus, first, derivative of the second, plus the second, x squared plus 6x plus 7, times the derivative of the first. Again, go term by term. Cubic, bring down the 3, multiply it by the constant 2, and you get 6x squared, plus the derivative of 3x is 3, plus the derivative of 5, well, that's a constant, so it's 0. And now, I am actually completely fine for the purposes of this with you leaving your answer just like that. First derivative of second plus second derivative of first. Ultimately, when we do applications and we have problems like this, you'll have to FOIL them out and solve them out. So I know you'll get practice with that and I'll be able to test and see if you can do that. If you want to FOIL it all out and combine like terms, you can. You don't have to. If you ultimately want to test yourself, do this both ways. FOIL this and then apply the power rule term by term. Or product rule, then FOIL these, combine like terms, make sure you get the answer the same way for both of them. I don't really care as long as you can find the derivative. I would point out though, if you're testing yourself against the problems in the book might have their answers right differently than you would. They may use this, say this rule right here and FOIL stuff out. They may not. Also with WebAssign, they may tell you, write your answer in this form versus that form. I don't really care about that all that much. If it's important, I will explicitly tell you what to do. But just be aware. I remember when I was in school, our instructor would give us odd numbered problems. All of you know odd numbered problems always have answers in the back of the book. He would give us odd numbered problems to solve for homework, and then he would say, get your answer, and then test yourself by looking at the answer in the back of the book and seeing if you could mathematically make your answer look like the answer in the book. Do all the different algebra tricks you know to make them look equivalent. So if you choose to do that, you can. And again, it is good practice and beneficial, and it helps strengthen your algebra. But I'm not going to really require that. I just want you for right now to be able to use the rules correctly. So right now, as far as derivatives go, we know the derivative of a constant is 0. We know the derivative of a linear function is the slope, which is the coefficient of the x term. We know the derivative of the quadratic x squared is 2x. And I know I can expand on that using the power rule. For any x to the n, I just bring the n down, and it becomes nx to the n minus 1. Bring the power down, lower the power by 1. You'll hear math people say that all the time because it's the power rule. We know if I have constant multiples in my problem, they just get multiplied through the derivative. They don't matter. And we have the product rule. The derivative of the product is the first times the derivative of the second plus the second times the derivative of the first. If you choose to do that backwards, that's fine. Ultimately, we're going to learn even more tricks, because the way this actually works is eventually, by the end of this class, we'll say, which for this class is not very long, we know that some functions are non-differentiable, even if they're only non-differentiable at certain points, like corners and cusps, vertical tangents, and all that. But any function that is differentiable everywhere, well, we want to be able to differentiate it. We want to be able to find its derivative. So now you can pretty much take the derivative, I'm going to assume, of any polynomial. Here, if I FOIL this out, it would become a polynomial. In combined like terms, it become a polynomial. So basically, with a combination of constant multiple rule, power rule, and product rule, I can take the derivative of any polynomial you can imagine. What about trig functions? They're continuous. There's no corners on those. Some trig functions are continuous on certain places. What about exponential functions, logarithmic functions? There's a lot of functions out there that you know about that we haven't talked about yet. But if you think about their graphs, they'll definitely be continuous, again, except for some trig functions. And those trig functions will be continuous in a lot of places, just at asymptotes they won't be. They won't have corners, they won't have cusps. So they're definitely differentiable, and they're important, and you can use them for applications. So ultimately, we want to be able to differentiate all of those too. And that's what we're going to spend the next couple of weeks on, finding every possible trick to be able to differentiate every type of differentiable function. So you want to learn these rules and practice them as much as possible. If you don't get enough practice through WebAssign and your textbook, feel free to either let me know and I can come up with more practice for you, or just Google calculus practice, fill in whatever rule you want to practice, and I'm sure you can find websites that'll generate them for you, because you want to know these rules inside out, forwards and backwards, so that we can differentiate every function that is differentiable.